Well, hello and welcome everyone to the informational webinar on IPAM Spring 2025 long program on non-commutative optimal transport. We're holding this Zoom call to inform you of the format of an IPAM long program and what you can expect as a long program core participant or a participant in a given workshop of the program. And to provide you an opportunity to hear from the program's organizers who will give an overview of this program's scientific focus. And we'll also go over the workshops, the scientific focus of the workshops that are scheduled. The order of this session is the following. I'm going to introduce the organizers very briefly and say a few words about IPAM and our mission. Then the organizers will discuss the overview of the program and the workshops. And at the end, I'll also give more information about the general format of the long program, what you can expect as a core participant then, and we'll open up for questions if there are any questions in the chat. So I do ask if you have a couple of questions that come up to please put them in the chat, and Karen will let us know towards the end, what questions we have. Great. So let me click correctly. As you know, IPAM is one of several NSF-funded mathematical sciences research institutes. We're housed on the beautiful campus of UCLA. Our tagline is "Math changes everything." It is our mission to bring together researchers in mathematics and other disciplines, and also mathematicians within different subdisciplines to create research communities, to build new interdisciplinary research opportunities as well. So we build communities and collaborations. We break down linguistic barriers to ensure that there's a common language, and we'll talk specifically about how we do that for long programs. And we also, of course, just highlight important mathematical problems and issues and explore possible approaches through all of our workshops, long programs, RIPS programs, and so on. So I'll talk a little bit about how we do this. We also, again, develop human resources and highlight mathematics as a viable career path from undergraduate to graduate, postdoc, and on. Promote use of mathematics as a driving force for innovation, and engage and transform the world through mathematics. It is our goal to drive applications and math research. Great. So here is a list of our scientific directorate at IPAM. So Dima Shatenko is our director. Christian Roche is the deputy director. I am Selenne Bañuelos, the associate director. And Stan Osher is the current director of special programs. So IPAM's scientific leadership is responsible for planning and executing all of the science activities at IPAM. Before and during your visit at IPAM, you will also be supported by our great IT staff, our videographer who's on the call as well, our financial staff. We have a great program staff as well. Karen is on this call now. She is the lead program manager for this program. And we also, of course, have a chief administrative officer. So you'll be hearing from all of our staff members, again, prior to your visit, as we collect information, and then as you collect information about, how to actually be here in person and schedules and so on. So you'll be hearing from all of us. Great. So I've briefly described our mission, and one very effective way we achieve this mission is by supporting these 14-week-long programs. So we have 2 long programs. Each of them are 3 months. We also have workshops and exploratory workshops within a long program and standalone. And we are year-round. So as you can see from here, so we are a year-round institute. So we run, say, for example, beginning of the year, January through March, we have standalone workshops. March through late June, have a long program. In the summer, we have this research opportunity for undergraduates and graduate students elsewhere. And then we have another long program in the spring. So we are year-round, and we have industry short courses as well, and other outreach and workforce development programs. We serve the mathematical community, but as we mentioned before, we're very interested in making sure that we bridge gaps between mathematics and other sciences. So as you can see from this list here, about 54% of our participants are from mathematics or statistics, but our participants also have like a broad background. Particularly, this program will have people from computer science and chemistry as well, engineering and so on. So this is just an example that, again, we do serve the larger research community. But today here, we're going to talk about the long program on non-commutative optimal transport. So this program is going to run this upcoming spring. Very excited to welcome everybody here at IPAM in person on March 10th for opening day. So I'll go over all of the nitty gritties of what to expect for the structure of the program. So again, we are here to speak about non-commutative optimal transport, and I'm going to punt this off to one of the lead organizers, Augusto.
Selena, thank you very much. So can you hear me?
Yes.
So fantastic. So let me try to give like a very brief overview about like non-commutative optimal transport. But like before getting to non-commutative, let's talk about like quantum optimal transport theory. So like optimal transport is a very well established field from mathematics and economics that flourished mainly in the 90s thanks to the works of like Jan Brenier, Robert McCann, Wilfried Gangbo, and it was a theory that like was very successful and had many applications like within and beyond the mathematics. So first like in geophysics, geometry, economics, but like more nowadays in other physics like quantum physics, quantum chemistry, and machine learning. So like in classical optimal transport theory, so like optimal transport theory for probability distributions, so like there are many different formulations, like a formulation that we say that is static, that is like is the Monge-Kantorovich formulation. The formulation that's said to be dynamical, or like is also very well known as like the Benamou-Brenier formulation. And also like more recent, like after the seminal paper of Marco Couturi in 13, so like a lot of like other aspects of the theory, such as computational, statistical, and machine learning methods has been developed in the last years. So like the next slide is going to show a little bit like some examples of development on those areas. So like from pure and applied mathematics, but also beyond like machine learning, like generative models and like statistical inference in vast time space. But what is very interesting in this like picture of optimal transport for probability distributions is that like all those different formulations, static or dynamical, they are all equivalent to each other. And also like many computational algorithms nowadays, like theoretical guarantees of convergence, robustness of those algorithms are very well understood, and they are strictly related to the theory. So like I would say that like this picture, like at least at a certain extent, is super clear to all of us. And in the next slide, like just to try to exemplify like the amount of research that has been done in the previous years. So like in the last 5 years, we had at least 5 new books about optimal transport. So like just to cite a few of them. So one by Francesco Maggi, the other one about Ambrosio, Semolo, and Bruet, like another one by Alessio Figali and Glaudo. So like there has been a lot of activities in the recent years. So I'm not mentioning the book about the statistical optimal transport by one of the workshop organizers, John Weed, that John Weed wrote. So there is a lot of activity on the classical theory of optimal transport for probability measures. But here, like we are taking a different direction. So a direction that has not been a lot explored yet, that is like optimal transport for density matrices and operators, or like optimal transport problems that came from motivated by problems of like a non-commutative probability theory. So that this is the next slide. So in the picture of like optimal transport for quantum data, so quantum data we can understand like density matrices or operators. So the picture is much more obscure. So like so I guess the next slide I have a timeline of, so like this theory was like it started in the 80s by the works of Konex and Virulescu, but only 10 years ago, like by the works of like Jan Maas and Eric Carlen, that like a theory for optimal transport in the non-commutative setting is started to be more actively developed until like our days. And like in the next slide, I show a little bit what are like a few glances of this development. So there is a community that includes Dario Trevisan, Giacomo Di Palma, François Gols, who generalized the optimal transport theory for probability measures in the non-commutative setting, but like generalizing the static formulation, so the Monge-Kantorovich formulation, and this leads like to a theory for like optimal transport for quantum channels, the equivalent of like the one Wasserstein distance in the non-commutative setting. And like completely independently, there was like several attempts to develop a non-commutative version of optimal transport based on the dynamical formulation, the Benamou-Benier formulation, or in the works of Carl and Maas, also like to understand like what is the equivalent of the well-known gradient flow structure, like the JKO or minimizing movements schema in the probability measure setting, like what is the equivalent in the non-commutative setting. And like even more recently, we start also looking into like computational algorithms for non-commutative optimal transport, links to operator tensor scaling, also like applications in machine learning, and also like non-commutative relaxations of like optimal transport problems for probability measures. But like what is very interesting, like all those theories of non-commutative optimal transport that generalizes one of the formulations of the classical setting may lead to different and divergent theories in the non-commutative setting. So like the picture in this context is much less understood. And like that's why we need a thematic program to stay all together and understand how to build the bridges between those areas. So, and one thing that I want to stress that is a little bit like I have two examples on the slide, is that like the kind of tools that we need to like to build the bridges between those three different formulations, or at least three different formulations in the non-commutative setting, those not necessarily come from optimal transport. So like in our core participants and also the organizers, like we have different types of expertise and skills. And like for the young people, I really want to encourage like people who have expertise in PDEs, geometry, operator theory, or even like random matrices. So there are a wide range of skills that we are looking for this program, like scientific computing and even skills in quantum chemistry, that can be very useful to make sure that like we can make progress to complete this picture. So, and just to say briefly, we are going to talk about the workshops lately, but like the workshops are organized in such a way of trying to provide a dialogue to making those bridges. So like, for example, workshop 1 is going to build a bridge between like the static formulation and computational algorithms. The workshop 2 focus more in the dynamical formulation. And I would say the workshop 3 is more, it is a bridge between classical and non-commutative, so like commutative and non-commutative optimal transport, which can make like a lot of connections, not only with the dynamical, but also with the static formulation. But of course, like the fun part, and I guess like the part where we are going to really make fundamental progress, like is beyond the workshops, when we have like the IPAM and we have the freedom to work and discuss among those open problems. And this is going to be organized in like an open problems and work group sections that we can talk a little bit more during this chat.
Great. Thank you so much, Augusto. And I'm going to go back to one of our very first slides because I totally skipped introducing all of our amazing organizers here. So again, the list of the people that are on this slide are the long program organizers. And we also, again, as Augusto mentioned, have 3 scheduled workshops. And the long program organizers are also helping with those workshops along with other collaborators as well. So on the call, we have Trifon Giorgio, who's at UC Irvine. Augusto, you just heard from Gerolin at University of Ottawa. We have Farnaz Zara at Queen's University. Sorry? Did I say something?
No, I just say hello, everyone.
Oh, hello. Yes, thank you. Alessandro Rudy, who is not on this call now, but you will, of course, hear from him here at IPAM. Dario Trevisan, he's at Universidad de Pisa, and Oliver Se at Eindhoven. So you'll hear from our wonderful organizers who are, again, very much dedicated to this long program, making sure that, you all have a great time while you're here, feel supported and mentored, and of course, have great research experience. So I'm going to jump back towards the slide on what we have scheduled, which is, as I mentioned before, the program begins with an opening day. This is on March 10th, 2025. This opening day is like an orientation. It will be held in Santa Monica, so it's actually not at IPAM. The idea is to have a more informal setting for everybody to get to know each other. Everyone who's here in the long program is going to have 2 minutes or so to introduce themselves, where you are in your research career, what is your current research focus, and what you hope to get out of the program. And we'll have, some talks just to kind of get us started for the rest of the program. Then the rest of the week, Tuesday through Friday, we'll have the tutorials that are going to be held here at IPAM. And as I mentioned previously, the tutorials are really meant to, they're not research talks, right? They're really meant to give every angle, as Augusto just spoke about, every angle of like the research project, and making sure that we all have, sort of common language when we're speaking about the topics in the long program. Then we have the 3 workshops that are scheduled. And again, these are not standalone workshops. These are workshops all meant to feed back into the long program and the culminating workshop. So I'll talk about the latter part and what to expect in between. But for now, I'm going to pass it off to Workshop 1 organizers who are here. This is, so Kasia is here and Dario, who will be speaking about Workshop 1.
Yeah, thanks, Selene. Maybe I just start and then Kasia, you can join. So about the first workshop, Augusto showed some very nice diagrams before. So workshop 1 focuses on, say, bridging the gap between the static theory of optimal transport, actually the static theories, because as Augusto said, there are plenty of different ways one can explore this non-commutative transport theories, but on the other side, also the numerical side. So we want to understand whether we can implement efficient algorithms, so we can mimic or understand what are the differences between the classical and the possible quantum counterparts of these algorithms. As you may see, so we have a 1-week workshop, so it will be, say, focused on these particular problems, because there are plenty of open problems on this side. For example, just to mention, maybe then Kasia can also discuss a bit the possible applications, but inside the mathematical, say, realm, we want to understand whether different points of view may have advantages or disadvantages from the computational side. For example, there are operator and tensor scaling algorithms that are very promising to be applied for quantum optimal transport, but on the other side, their convergence or extensions to infinite dimensional, so full operator settings are not much understood. On the other side, there are plenty of applications, and before we mention the application in quantum chemistry, let me mention also that there has been a surge into applications in quantum machine learning. So quantum machine learning will not be really the focus on this workshop, but more on the mathematical side. But of course, there will be invited speakers who have worked, for example, in quantum so-called generative adversarial networks. So to learn quantum states from a small set of measurement, possibly. On the other side, there are also applications in quantum chemistry. So maybe I will leave the word to Kasia. She can maybe say some word on that.
Okay, thank you, Dario. So Dario has already said almost everything about the workshop, but just to complement. So as he said, this will be maybe the most interdisciplinary workshops of all 3, because we try to collect speakers from the field of mathematics, chemistry, quantum chemistry, and quantum physics. And the goal is, also Dario mentioned, is to make a bridge between all these 3 disciplines. And from the side of quantum chemistry, we would like to get some insight from the optimal transport theory of how to make advances in the density functional and density matrix functional theories. Just a few words of explanations. Most of you are familiar with the density functional theory, and you know that the main object there is the functional of the electron density. When it comes to reduced density matrix functional theory, which is a younger sister of the DFT, the main variable is one electron density matrix. And this is also a ground state theory. The hope is that with the density matrices, which includes more information than density, electron density, we can better describe strongly correlated systems. So, as I said, by hearing the talks focused on the DFT and reduced density matrices, also other methods based on reduced density matrices, and on the other hand, on non-optimal transport theories, we hope to get some insight and maybe foster some collaborations between scientists from all these fields with the efforts to advance all the fields. But my focus would be on density and density matrix functional theories.
Thank you. Thank you both.
Thank you.
Great. So now for workshop 2, we have here on the call Trifon and Oliver.
Oliver,
Yes, I'll start and then I'll hand it over to Trifon. So workshop 1 is highly recommended. Yeah. Okay, so the second workshop will be about the density or the dynamics of density operators, organized by Trifon, Léonard Massageon, and myself. In line with the theme of the long program, the second workshop serves to focus the past, the future developments of non-commutative optimal transport, pretty much all the things that Augusto mentioned earlier. But here we want to also kind of look into quantum evolutions, hopefully see the links between optimization, grain flows on the one hand and non-commutative geometry on the other, and see how it impacts quantum theory, and also to explore open questions and future directions. Also, as Augusto pointed out, the relevance of optimal transport has grown significantly across various disciplines. For us, we kind of take as a starting point, for instance, the work of John Kindler and Otto, which kind of brought major breakthrough in evolution equations and PDEs. So what they essentially did was express the Fokker-Planck equation as a grain flow of the free energy with respect to some optimal transport metric, which is the Wasserstein distance. And this gave rise to kind of a geometric interpretation of the Fokker-Planck equation. And this transformation not only led to new insights of geometric evolutions, but it also breached fields like geometry, information theory, and also thermodynamics. Based on that, we believe we are now at the stage where we can explore, or we are able to explore similar links and structures in the non-commutative world. So therefore, we kind of came up with this idea of this workshop. And why do we think so? Is because in the last 30 years or so, different approaches for non-commutative optimal transport have emerged, or non-commutative geometry have emerged, both the static and dynamic, with the intention of geometrifying non-commutative processes, also mentioned earlier by Augusto. And this includes, and not limited to, frameworks inspired by classical optimal transport, but adapted somehow to fit the structure of quantum mechanics. That being said, there are many, many open questions. Questions like, do these different approaches have something in common? Is there a unifying principle? And more practical, can it help us better understand quantum physics, provide new insights, such as predicting new physical properties or natural timescales for quantum processes? Can these be used to derive fundamental principles in quantum theory? Do the structures in fact help? So personally, I think the prospect, just from the mathematical perspective, bringing optimization, geometry, quantum information, and quantum thermodynamics together via non-commutative optimal transport is super exciting. I think if we have such a marriage, then this could lead somehow entirely to a new paradigm to help us understand quantum systems, including dynamics of open quantum systems, the role of entropy in quantum processes, and the behavior of quantum states over time. So with so many unanswered questions, we hope that this workshop will inspire fresh ideas, input from experts across different fields. So we have mathematicians, physicists, mathematical physicists coming together to discuss and to bring, we want to bring all these different perspectives to make progress, identify new paths forward. And ultimately, we hope that non-commutative OT can become a key tool for studying quantum evolutions with big implications, both theory and in practice. Trifon, you have anything to add?
Yeah, I just wanted to say a few words also. Thank you all. I wanted to echo what was just said, and Augusto and Oliver and everyone else. The general theme of the program is a vibrant new field. With the potential of bringing transformative insights in geometry, information sciences, and quantum systems. Just briefly, just to recap and give it some sort of an image of this. Optimal transport is basically comparing distributions. And it's not simply how different they are, but exactly where the mass is distributed, how you move from one to the other. And as a result, it provides this natural metric, the Wasserstein metric, which is weakly continuous. So the interpolation between one and the other, it gives you the natural sort of flow of the mass and avoids push-pop phenomenon. And that's why it was so much of use, for example, in computer graphics, computer imaging, and so forth in the 90s, with very, very many developments in engineering. Now, the transformative stage that led us to non-commutative has its roots also in the 90s, Alan Kohns, many others. And also in signal processing, you have, for example, matrix valued stochastic processes where you have matrix distributions and you like to know how different they are. So it's not just where the power of a signal is, but also you have some rotations involved. So that brings us to thinking of optimal transport of matrix value distributions. The most natural thing is quantum. So you have density matrices. So there's a static, there's dynamic formulation as it was discussed. And again, the guiding paradigm for the second workshop is this remarkable result of Jordan Kindler and Otto that link information theory, namely entropy, the Wasserstein metric, the optimal transport metric, and as gradient flow, the heat equation. Why all these three things come together on the same table is quite remarkable. And in the classical setting, just to stay a little bit more there, it turns out that the Wasserstein length quantifies dissipation for stochastic thermodynamic systems. And as such, it has been used to quantify, for example, power that can be drawn out of temperature gradients. So there is a whole new world now in quantum thermodynamics, and then quantum transport, how you link quantum systems. And Eric Carlin and others several years back tried to lay out the foundations for this. And there is a zoo of possibilities, very much like in quantum information. There are many different, even notions of entropy. So all of that needs to be explored. And we are at the cusp of great many developments that will give a new angle to this whole edifice. I just wanted to make a mention here. The picture of this particular workshop there is a Wigner function for a spin half particle, and that brings a whole new angle to this discussion we're having, because Wigner functions and other quasi distributions represent equally well a quantum system as a density matrix, and they look more classical, except they are positive and negative. And the transport of that is very, very appealing, because now you are in a more classical looking setting. So gradient flows in this setting is very attractive to consider, and some things are being done as we speak, but many, many more questions remain for everybody to bring up and explore together, pause and cross-fertilize ideas about different fields for applications, theory, mathematics, information, and everything will come together. It's actually fascinating program, and I think we are all very, very excited. I'll stop here.
Thank you. Thank you again to Oliver and Trifon. So over to workshop 3. I believe Augusto is going to be introducing us to workshop 3. On the organizing committee is Quentin Berthet, Jonathan Nelsweed, and Alessandro Rudi. Alessandro, as we mentioned, is in the long program organizing committee, but wasn't able to be here today.
Okay, so I'm going to say like very briefly what are the goals of workshop 3. So like trying to represent Alessandro on this. So I guess like this workshop 3 is going to be like it will dialogue a lot with like workshop 1, but like at this stage. So since this is a very early stage theory, so we are solving many fundamental questions in non-optimal transport theory. So I think that like workshop 3 will have like a great component of like optimal transport for probability distributions, and like the recent developments in both computational algorithms and statistical optimal transport, with an eye towards a non-commutative optimal transport, in particular like presenting like recent developments in the fields, like using, for example, the semi-definite relaxation of optimal transport, and like computational algorithms that build up on this semi-definite relaxation. So I think that like there will be a good mix of like recent activity for the classical theory of optimal transport, and like an eye for like mid-term and like long-term goals, when like we'll be in position to develop like statisticals and more rigorous computational algorithms for computational optimal transport. So I think like workshop 3 mix a little bit of like the state of art of the classical theory, and have an eye like what is the direction that we can go towards like the non-commutative of OT theory.
Great, thank you, Augusto. So that's again a brief overview of the 3 workshops that are currently scheduled during the long program. But of course, there's also during the long program, there's time to bring in other speakers, or even like a hot topic or something like this that we've already been talking about as an organizing committee. But I'd like to again take the rest of the time here to talk about what you can expect during the long program. So first of all, like we generally have 40 to 45 core participants that stay at IPAM for the 14 weeks of the program. We have our own building on the UCLA campus. It's a really nice space meant to create a welcoming environment for collaboration. So there's plenty of open spaces in the building, whiteboards all over the place. There's also like patios and all that like in the building. And as I mentioned, we have office spaces for 40 to 45 participants that stay here during the entire program. The length of stay may vary for some, but this is primarily for those with labs at their home institutions. As I mentioned, we have programs here that welcome chemists and biologists and so on that need to go back and tend to their labs or have other pressing matters. But for the most part, our aim is to have people here the entire time, especially for our to help mentor and guide our graduate and postdoc students. Another really important thing to note about the long program is that this is not open for registration. Everyone who is interested needs to apply and then be in. They need to apply to then get funding to be here, long-term housing and travel, and are automatically registered for all the workshops that are in the long program. But also we send out invitations to other more senior researchers that we want to make sure are here, that we can talk to, make sure that they're here during the program. So as you can see from this diagram here, the 14 weeks of the program starts with the orientation or the opening day, which I mentioned a bit ago, the tutorials week, which I also mentioned a bit ago, and the workshops. There are usually 3 or 4 workshops during a given long program. At the very end of the program, we have the culminating retreat as well. So let me move on to the next slide to discuss those. So during a long program, working groups are formed. So this is some way to provide structure during the off workshop weeks, which many of our participants have said are the highlight of their time here, because that's when you actually get a chance to work and collaborate with people and actually move forward with your work, because the workshops are they're like mini conferences. They're very packed schedules, right, from 9 to 5 kind of thing. But the off workshop weeks is where the magic really happens, where you all get to work and collaborate here while you're at IPAM. But a way to provide the structure is after the tutorials week, we all get in the lecture room and sit and talk about what sort of open questions, what are things that you are all interested in tackling. And we form about 10 to 15 groups, and then organically as the program goes on, some of these groups might merge, some of them might die out and so on, but there are still, again, opportunities for y'all to collaborate and form new collaborations here. We also ask our junior participants, or really anyone who's at IPAM for the long program who's not scheduled to give a talk during a workshop, to speak while they are here. And during these the seminar series is formed again during the off workshop weeks. And it's, again, pretty low key setting where we're all those who are here in the building join. But we really do emphasize that we would like everybody to have the opportunity to speak. And it doesn't have to be, directly related to the topics here at the long program, but, maybe just what you are working on now. If there's a paper that you're currently reading that you just want to understand better, perfect setting to do this kind of thing where, you take, 30 minutes, an hour to present that work. And as I mentioned, the core participants that are here, they represent each stream of the program. So we have quantum chemists that are going to be here, mathematicians, mathematical physicists, and so on. And the senior scientists are from academia, government, industry as well. They're here to provide leadership and mentoring for our more junior participants. So again, I really do want to emphasize that, like, the most of the work happens, the time that you actually move forward on your research specifically happens during the non-workshop weeks. Great. And I briefly mentioned the culminating workshop before. This is a really important time. This is the very last week of the program. This is by invitation as well. So those who are here an extended period of time are invited to the culminating retreat. This is held up in Lake Arrowhead at the UCLA Lake Arrowhead Lodge. It's the opportunity to, the way I like to think about it, is just like tie the bow on the program, take stock on what was learned, and really like give an outlook right into the future of where is this research area going? What kind of, if your working group got to a point where you have a question to pose out to the world, that is great. We want to hear about it. NSF wants to hear about it, because again, our job is to help create these new research communities. After the long program is over, again, this is a 14-week long program, but about a year and a half after, you would be reinvited for a reunion number 1, and then a year after that, reunion number 2. So there are opportunities to continue these collaborations. Our job is to help foster that collaboration. So it's a long-term goal, right? Something that we want to maintain. So we do that via the reunions. Great. So as I mentioned, if you're interested in attending the long program as a core participant, you need to apply for that. Go to the application tab of the webpage. So you just go to our long programs and look for the title of this long program. And there's an application tab there for that long program. You'll submit a CV, and we require letters for more junior participants. In particular, we want to know, for example, that your advisor knows that you're applying to be at a long program, and that, that they're okay with it. But as far as the form of the application and what you will communicate to us and the organizers is, why do you want to attend this program? How, does your research overlap with some of the themes here in the program? And if not, that is totally fine as well. If your goal is to get into this research area, what have you done so far to get into it, and how do you hope that this program will help? How can you contribute and or benefit from the program? So those are the kinds of things that we ask that you submit in the application. But the workshops, however, so the workshops are open registration. If you just want to attend a workshop, you can register for that. You can also apply for funding for a particular workshop. So if you go into the page, let me go back a slide. So if you go to the activities tab of the long program, you'll see a list there of the workshops. Each of those has its own webpage. So you'll click on one of those links, and each of those has its own application tab. So you'll go onto a workshop application page and apply for funding there. So typically, the funding that we offer for an applicant is in the form of housing, which in Los Angeles, amounts. You have a single hotel room, which amounts to about $1,200 during your stay. Every Monday, the first day of a workshop, we have a poster session. So we invite all of our participants to present a poster. If you're here as a core participant, we invite you to present a poster multiple times if your research, again, is aligned with the different themes of on those workshops. And we have the program webpage here. And any questions? Thank you all for your time, by the way. And any questions? Do we have any questions on the chat, Karen? Sorry.
I see that Augusto has raised his hand.
Oh, yes.
But yes.
So just to try to break the ice, why people are thinking about the questions or get encouraged to the question. I see many people that I don't know that are in this room. So please, ask as many questions as you want. So what I just want to say is that I have been in IPAM as a PhD student and also as a postdoc. So for me, it's very nice to be in IPAM, organizing a program. And I just want to stress what Selene says. So I guess this is an amazing opportunity. So to diversify your research, to enter in a different research topic, working with people that has some experience in the field. So you don't need necessarily to be an expert in optimal transport. So this program requires a wide variety of skills that also the team of organizers do not have. So you are more than welcome to submit your application to explain us why you are interested on that and what are your background, because our idea is try to form collaborative teams where we try to do a type of research that we could not do by ourselves, but by creating teams with complementary expertise. So any applications are more than welcome, and I think that these at least for me as a PhD student and a postdoc changed completely my career path. So I had a wonderful experience at IPAM that had a huge impact in my career. So I think particularly if you are young, you should really consider to do this, but also more senior professors who want to diversify a little bit their research and starting help us on building this field, you are also more than welcome to apply. So we are a diverse group of professors and researchers, diverse scientifically, but more in a broad sense. And we are really looking to a diverse group of participants outside our bubbles. So we really are looking to people who are not necessarily in our bubbles.
Great. Yes. Yeah. Thank you. Thank you for mentioning that, Augusto. I meant to say that Augusto is again a great organizer just in general, but in particular with IPAM, it's he comes with the experience of being here as a participant himself, as a grad student and postdoc, and now is organizing a long program. So understands, the what our general structure is of an IPAM long program and how to help mentor our students that are here. So great. So we do have a question for Spencer. Hi, Spencer. I think Augusto, if you may want to take this.
So I can go for this question. So probably I can go to the first one. When we go to computational methods in quantum computing, I probably leave to Dario or Oliver. I don't know who want to go for this. But what I'm saying, the computational, as far as I know, solving at least the static formulation of quantum optimal transport, for example, if you look to the equivalent of the two vast time distance, this is equivalent of a semi-definite programming. And at least in this setting, there is a lot of the literature, in optimization and computer science. But the type of application that we are looking at, we need to develop new ideas and go in different directions. So specifically, one of the applications that I have in mind is quantum optimal transport divergence, for example, for quantum channels, and also in electronic structure theory, what Kasia mentioned previously, the reduced density matrix. And then there are a new technology that has been developed that is not based on semi-definite programming, but from now we are basically working like on proof of principles. So like, and the goal at the workshop is that like we are able to scale this algorithm to, for example, quantum chemistry or quantum information applications. But like the theory of quantum optimal transport, like computational quantum optimal transport, is in an even more early stage than the theory of quantum optimal transport itself. So like there is a lot to do. I don't know if Dario and Dario and Oliver, you wanna go for the second question on quantum computing?
Can I
Yeah.
say something about
Okay.
computation?
You go.
Augusto, can I say something about computations?
Of course.
Yes. So I want to echo that this is in early phases. And I wanted to make the following remark, that in classical optimal transport, which is a linear programming problem, and Kantorovich showed that, and he got the Nobel Prize for his work and so on and so forth, the classical optimal transport. The computational aspects took a long time to be sorted out for very large problems. So then there were methods in early 2000, and then there was this simple idea, and Couturi brought it up, which was basically the standard interior point methods. You have a regularizer, and then you solve linear programming problem a little bit faster. And this idea actually goes back 100 years to Schrodinger, something called Schrodinger bridges with connections to large deviations and so forth. So this regularization of optimal mass transport has very great roots in probability theory, and now it's the bread and butter on how you compute. The analog for quantum is wide open. There are quantum Schrodinger bridges. There are sort of some connections with large deviation theory, but not quite. So all of that is in its infancy, leaving aside what is the best way to compute. What is there could be new regularization methods that could accelerate things, but more than that, there is physical theory behind and connections to information theory. So that's what I wanted to say.
Maybe can I add just a word? One should also remark that there are many approaches to quantum optimal transport, and so far, as you said, all of them on the side of computations are on very early stages. So it might be that some approaches are more suitable than others, or allow for better algorithms. So in this sense, this must be really explored, and of course, we need a variety of people, because me myself, I know I don't qualify as a computational or applied mathematician. So we are really excited for this time at IPAM, where we can join forces essentially.
Maybe I can echo a little bit on the side of quantum computing. So if I'm not mistaken, I don't believe that there are any, so at least physicists are not using quantum optimal transport directly to work on quantum computers at the moment. But they are, of course, on the algorithmic side, there are implementations of optimal transport tools. So quantum optimal transport, Dario, for instance, is one of those people that have used quantum optimal transport to kind of break through the barrier of this Baron plateau problems that people in variational quantum algorithms have issues with. So this is possibly a use. Of course, the implementation is at the moment still on the classical computer and not directly on the quantum computer. So I think there is still a lot of progress needed to transform these algorithms to work directly on the quantum computer, and with some hope that you will not have the issues of scaling and stuff like that. So just echoing, it's still wide open.
Great. And excuse me, we have a question from another participant, is what is the expected percentage of math in the workshop? Again, I mean, it is a math institute, and our whole goal here is to bring in different research domain sciences with mathematics, but it is a collaborative setting, right? So yeah, I would say expect mathematics during the entire program, but your area may not be specifically in math, but how you contribute to it is important. Augusto, you want to add anything to that comment?
I guess that's perfect. So it's very hard to tell you a percent, but like I guess our philosophy is that like I don't know, at least what most of us know what to do is like convert a problem from science into a math question. So that is you should expect in the program, that like we believe that like we needed to solve a math problem to make impact in computational science and science in general. So these are our expertise, but like we wanna build the collaborative teams, as I said before. So it's very important to have like expertise from a specific field, quantum information, quantum chemistry, machine learning, to be able to solve the mathematical and computational problems that we're looking at. So I guess that is the general spirit, and like I echo what Selene said.
Great. And we have another question of like what is expected from PhD students, and then should we directly discuss with some of the organizers the work that you're interested in? I would say, I mean, you can find the list of organizers on the webpage, right? You can email them, but ultimately though, like it's your application, right, that we're going to be looking at. So the application that you submit, where you get to put down your research interests and so on. What is expected from PhD students? Well, in terms of the application, I just went through that, making sure, of course, a letter of recommendation is very important. At least one, I would say two, though, for a graduate student would be best. But what is expected from PhD students during the program is, well, to be here, be engaged, be open to working with others is very important. Again, like give talks, just be collaborative. We don't expect you to say lead as a senior researcher would, but of course, as we always, there are always opportunities for leadership. So if you can help organize the seminar, or you can just, help steer your group and making sure that you're meeting often, things like this. But yeah, so in terms of what is expected from a PhD student during the program is just to be here, be engaged. And we do expect, by the way, PhD students to be here the entire program. We do not, it is very, very rare, in fact, for a graduate student to be here for only a few weeks or something, because again, it's just, well, on the technical side here at UCLA, we have to file other paperwork for graduate students to be here, number one. But then also, you as a graduate student, what you would actually get out of the program, you really need to be here for an extended period of time. Yes. Great.
Can I say something?
Yes, please.
Yes. So what's expected of a PhD student? I think it's as much as you put in, you're going to get out, and the whole program will get out. You have to be active. You have to challenge whatever you hear. Someone gives a talk. Be engaged. Ask questions. Challenge the speaker, and challenge each other. We go in front of the board and we just throwing ideas and look at directions, and then that's the path to discovery. And the more active you are, whenever you're in the program, you put your heart and soul in this, and things come out like magic. And in terms of math, it's very, very significant part is math. Some physical intuition is also very important. Sometimes, it's a combination of things that drives you. And we are all different. We all bring something different to the table, and it's exactly the confluence of ideas and exchanges that create new knowledge. And that's what I want to say. And each of us would be very happy to engage with an email or anything if you have further questions on specifics, etc. So thank you.
Great. Well, that concludes our webinar. I want to again thank everybody so much for being here, for taking the time to join us. This is being recorded, as you saw when you joined the call, and will be posted on our webpage. So, you can look at this later, or those who are interested will be led to the recording as well. I want to thank the organizers again for your time, for being here, for sharing your knowledge. And as you can tell, everybody on this call and watching the recording, the organizers are very much engaged and very excited, and look forward to meeting you all here for the long program. So March 10, 2025. See you all here. Thank you.
Thank you, Selene.
Bye. Thank you, Selene.
Thank you, Selene. And thank you, everybody, for joining.
Thanks, everyone.
Thank you.
Thanks a lot.
Thank you. Thank you. Goodbye.